Hello, everyone, and welcome to the regular R&D talk. That's the series of sessions where R&D experts and enthusiasts, as well as honorable guests, share their insights to the newest technology and the impact of those technology on the businesses and humanity in general. So, agents and AI agents in general, as well, change the world today, and there are no industries that are an exception. Today's session will be focused on applying this novel technology in the energy and oil and gas specifically industry and showing its potential um, uh, within the steps that we as SoftServe gone through. As typically we are, feel free to share your questions in the chat and we will respond for them in the end of the session. And to start, let me introduce our today's speakers. So, Hatem Nazar is our global leader in energy and digital oil field domain, who advised major companies all over the world, including Shell, Saudi Aramco, and others, and has more than 30 publications in this domain, holding the PhD degree. Vladislav Selotkin is computer vision R&D lead at SoftServe, leading the team of AI experts who are transforming the way the computer vision algorithms as well as AI agent in that specific domain applied to our customers. So without further ado, transferring the word to the Hatem to kick off today's session. Hatem, over to you.
Thank you, Bodan. Thank you. Thank you very much. And welcome, everybody. Thank you for joining us, taking part of your precious time today to join us in this talk. The agenda for this is going to focus on two aspects, pretty much. You see the agenda here, but number one is why I'm going to describe why this technology matter. Why this is so relevant to us. Why this agentic technology and Gen AI technology is going to take us to the true next level in the upstream oil and gas business. And then the second part is Vladislav, my colleague, is going to go into the specific use case, how we work specifically on the area of seismic data processing. So let's go to the next slide. First thing I want to tell you, describe to you, is the issue of the challenges in the industry. The industry has been, going through some interesting periods in the last few years. But there are some challenges been going on for a long time. First and foremost is reservoir recovery. Reservoir recovery is a big challenge in our business. It is one of the most important aspects. Oil companies are basically valued based on their how much they have in the reservoir. This is the value of any oil company around the world. And reservoir recovery has been challenging. Worldwide today, we are probably on the average less than 40%, right? Meaning if you find a reservoir of hydrocarbon, typically oil, let's say, for instance, and you have 1 billion barrels of oil there, we're only able to get 400 million barrels. That means we have 60%, 600 million barrels staying in the ground. So that is a huge challenge, and we've been working for years. We have a lot of technologies applying to this, and some parts of the world are better than others, but it is a challenge. So we're doing our best to improve reservoir recovery. And the other challenge is that we are in a period right now where fewer major discoveries. In the last 8 decades, we're probably at the lowest level. Operating costs are becoming an issue right now. We have a lot of pressure on break-even prices. Commodity prices is low, so we're trying to make the most out of existing production. Managing production also, we have a lot of existing wells and existing fields where you have the decline in the pressure and you have water cut increases. All these challenges are bringing a lot of imperative on applying newer and newer technologies to improve production from existing assets. Knowledge management has become a serious issue in our industry, believe it or not. We have a lot of experts that are retiring. We have one of the highest industries in terms of age bracket. And also, we have a talent shift. People are going to work in other areas, other technologies, and we're seeing a decline in petroleum engineering enrollment and graduation. And a lot of technologies that we have used in the past, they're great. They're really made a huge impact, but their performance is sort of plateauing in terms of giving us more data and more information and more insights. So these are important things to keep in mind. Let's go to the next slide, Vladislav. So here I want to bring up some idea to you why this technology, this agentic AI technology is so impactful. Because I want to revisit here some of the greatest technological advancements that we've had in the last few decades. For instance, 3D seismic changed everything. In the 90s, when we went from 2D to 3D seismic, the impact was huge in terms of the value. I mean, and still to today, we're benefiting from those technologies. Rotary steerable drilling, horizontal multilateral drilling was huge. Instead of drilling a vertical well, now we can go horizontal, and from one single drilling location, we can go into multiple places, as you can see here, left, right, so hydraulic fracturing, this is what we call fracking or, especially applied in shale. This was huge. As a matter of fact, I want to bring up the fact that things like hydraulic fracturing were developed in the 80s. It took 20 years for us to realize the value of this technology. Enhanced oil recovery, SCADA automation, all of this made huge, huge impact that is not in the billions, but literally in the trillions of dollars. I want to show you some number here in the next slide. If you don't mind, go to the next slide, Vladislav. So here, for instance, horizontal, we estimate almost 6 to 7 trillion dollars of cumulative economic value from one single technology. The same thing when it comes to seismic, all right? Seismic improved almost 15 to 20% from what we were getting from 2D seismic. So this is delivered almost 50 billion barrels of equivalent oil. The same thing, rotary steerable drilling. So these technologies, when we talk about the next generation of technologies, I think we are at the cusp of another huge step forward. And that's why I want to bring up these numbers to you because we think AI qualifies in that category. Next slide, please. So, you know, this is a game-changing technology. Why? Okay, let's go to the next slide. Everything that we do in the oil and gas, everything. If you talk to any petroleum engineer, doesn't matter whether you are working on exploration, on drilling, on production, no matter what, every day we're running a workflow. That's all we do, frankly. Whether you're running history matching or reservoir models, you're doing geosteering and drilling, whether you're processing seismic data, whether you're doing water flood management. This is all we're running workflows. And these workflows are extremely complex, extremely time consuming, and very demanding and require a lot of expertise, to run these workflows. So we need to automate these workflows. I spent actually almost, before I worked for SoftServe, almost a decade of my life just on the issue of workflow automation. Okay, this is how important this business is. And agentic AI presents to us a really formidable opportunities to automate a lot of these workflows. And that's really the subject of our talk today. So go to the next slide, please. So seismic data processing, everybody, we say, yeah, it's important. Why it is important, right? Basically, it is the first step in giving you accurate subsurface imaging, telling you where the hydrocarbon is, right? Identifying the structural faults, where the hydrocarbon is trapped. This is your view of the subsurface. It is a very very confusing view. If you look at it, it's like, where's the oil? But, our experts, geophysicists, geoscientists, petrophysicists, they know where they're looking, what they're looking, the characteristics reduces, and very important, good seismic data processing reduces your exploration and drilling risk. Drilling is very expensive. You don't want to go and drill, for instance, if you want to drill, in an offshore, environment, you could be spending tens and tens and hundreds of millions of dollars and you may hit a dry well. So you want to increase the probability of success while you're drilling. And seismic is a key aspect of that. And also it enhances your reservoir characterization, the porosity of the formation, the lithology estimates, how the fractures are oriented, precise mapping of the sweet spot where the hydrocarbon is and where the bypass hydrocarbon. And it is very critical for reservoir modeling. You cannot do proper reservoir modeling and with enhancing the the certainty, and reducing uncertainty as a result, a reservoir model. And basically, it is a key step to how you do proper field development, meaning where do I drill next? How do I, develop my field? And so it is very important. And the ultimate impact could be huge. If you don't do it right, you could be really seriously taking a huge risk. The next slide, please. So when we talk about seismic is very complex. Okay, this is a simple, very simple picture of a 2D seismic. Okay? As a matter of fact, it is kind of color coded and everything, and shows really clearly where things are. But in the real world, it looks a lot more confusing. And this is only in a 3D seismic world. You have thousands and tens of thousands of these slices, that are stacked in a 3D seismic cube, right? So you have a lot of noise, right? You've heard the term signal to noise ratio. This is a key example where we have a lot of signal to noise ratios, okay? Massive data volume, terabytes and terabytes of data. Time consuming. No, I mean, this is probably where the first area where you need high performance computing, and you need, all the GPUs in the world and all the CPUs in the world when we're applying it to the oil and gas. This is a very, very complex environment, and it is, and the workflows are very time consuming. This is not something that you do, quickly. You don't do it in real time. It takes weeks and months of processing, and it requires, extensive domain expertise, right? Typically, some of the highest skilled people work on this stuff, right? The best geoscientists basically really know a lot more than your average person. So this requires, as a matter of fact, one of the main reasons this project that we're going to tell you about was done is to be able to capture the domain expertise of geoscientists, okay, as they process the data, because that we have fewer and fewer of these people, and we wanted to encode this knowledge. Next slide, please. So seismic data, seismic noise, so can vary. I mean, you might think, oh, I have one type of noise. So think about it, just random noise. You have different type of noises. You have time domain noise. You have transform domain. Multi-component, adaptive. So you have all sorts of things here. There's a little picture here showing you just what an ambient noise is versus when you have a truck driving over it. You have different kind. So noise is introduced from every aspects out there. So you have, and we're trying to figure out in this process where's the noise, how we can take it out so we can have a clearer image, right? So that's always your first type of step that you want to do while you're processing seismic data. So let's go to the next slide, please. So for instance, here in an offshore environment, you could have ships, ships, when you are acquiring seismic data, you get a lot of noise from the ship, from the engines of the ship. And the left-hand side, you can see here where the arrows are, where we were able to identify the pattern for ship noise, right? And here on the right-hand side, after we process the data, you can see we cleared some of this noise, some of this noise. So it is very complex. So you might think, okay, well, what about if I have other noise? This is precisely the point. You're trying to build a system where you can say, okay, for this type of noise, let me try these different methods, right? And for every type of noise, there are different techniques that you should apply that are very much designed to deal with those kind of noise characteristics more effectively. So the next slide here, we show some of these examples. So for each type of noise, there are various techniques, right? For denoising, all right? So for ground roll, for example, ground roll meaning trucks and type of vehicles like that. So what we call coherent surface noise. You have different techniques like what we call the FK technique, the Tau P technique. We have the polarization filtering. You have multiple surface type of internal. You have the SRME, type of technique. You have wave equation demultiple. We have predictive deconvolution. For random noise, we use the frequency-based deconvolution, curvelet, wavelet transform, tau p denoising, and on and on. I mean, this is like enormous. Think about it, you have such a huge menu of techniques that you can apply to different type of noise, and each one is, and sometimes what we do is we try different techniques, right? So you decide, okay, for this noise, let me try this, let me try that. So you go through this trial and error process. And this trial and error is very time consuming. And that's why these workflows are very, very much take a long time. And you need also, once you apply that, you need to say, okay, did that work? Right? So you see what I'm getting at. First of all, you have to decide what is the technique, what is the type of noise, what is the technique I want to utilize, and then even after that, you have to validate that what you did worked. And that's why we're going to get into this next session here with Vladislav, and he's going to explain to you how this workflow works. So let's go to the next slide, Vladislav. All right. So why agentic? All right. What is the bottom line? We think this technology could have tremendous impact on seismic data processing. First and foremost is it has the capability of doing, more accurate autonomous noise characterization, right? Where you can automate the parameter and tuning and the workflow optimization, right? You can have multi-agent collaboration. One agent can do this, another agent can do that, another agent can validate for you. And then, like I mentioned, one of the actually, believe it or not, the main reasons we were doing what we were doing with our partner here is to encode the knowledge of experts. Take that information, build it into that knowledge base and think about now the agentic system becomes your geoscientist, all right? Eventually, right? And a reduction in the process time cycle. Basically, instead of having to take months, we can take maybe weeks, certain things, maybe we can take days. And accelerating the ML denoiser and continuous learning. We're building this so that we can continuously build our knowledge base. And eventually, you want these agents to continue to learn, right? So you run a scenario, you run it on this example, that example, on this data set, that data set, and the knowledge base continues to grow. So this is what we are working towards eventually. And the project that we are going to share with you basically shows a lot of promise in that direction, right? We're not claiming at all that we solve all the problems, but we really learned quite a bit, and the promise is phenomenal. I think there is no question that the industry is going to be doing a lot more of this technology in the future. Next slide, please. So I'm going to hand it over in 1 second to my partner Vladislav, who's actually I give him a lot of credit. He did a lot of the technical work. We had a great team. It was a very collaborative team. As a matter of fact, this is an amazing example how technology companies like us and service companies like SoftServe can work in a collaboration with an oil and gas company, and where it was a true team effort. Both sides were quite involved in every aspect, and it was really a true joint solution, if you want it. They were giving us the information, we were building stuff, they were reviewing it, they were recommending some changes, and it was really evolved into a tremendous case study. So with that, I'm going to hand it off to Vladislav, and so you go ahead, my friend, and go over the best part of
Yeah,
this presentation.
thank you. And yeah, basically, let's figure out why we actually need it and how we implemented it for seismic data processing problem. So the main problem as already Hatem mentioned, that seismic processing is the area where the knowledge of the geophysicist has accumulated for many decades. But mainly this knowledge is rarely captured formally. It basically lives in the brains and intuition of the experts, and where experts examines every seismic data slice and analyze it visually and decides whether it's coherent or random type of noise, how they can balance the signal to preserve the real seismic data and remove the noise. And this is kind of the main problem. And by applying agentic AI to this problem, we can basically solve different issues that have in the industry, like aging of the workflows, also knowledge transfer between different experts, also uh, speed up of the processing process, because usually it involves hundreds of micro decisions on every step of the processing pipeline, and you need to go through different validations and quality control and algorithm selections, and it can go on and on for a very long time. And basically, Agentic AI provides a kind of workflow where each decision point can be replicated, made explainable, and continuously improved. And in our solution, we basically did it by modeling different expert roles as independent agents. For example, noise detection agent that acts like a geophysicist, actually, who performs first pass of quality control and evaluation of the seismic data. Parameter optimization agent that basically behaves like more uh, signal processing expert who has access to different denoising tools and can tune the parameters of those tools. And the last one is a quality control agent that evaluates whether the current output is good enough or need to be updated again. And basically, this is the first time we can kind of codify or embed into code the knowledge of and the behavior of the experts, and in kind of a scalable and repeatable way. And yeah, we will go through the approach and how we did it actually. The first thing that we do for the POC, we have selected a publicly available dataset from the SEG wiki collection. And this dataset includes 3D seismic volumes from the New Zealand Parihaka area. And this volume basically contains very rich geological structure and represents real-world complexity and real-world example of the seismic data. And also to simulate kind of different noisy conditions, we built a noise generation pipeline, and we have injected Gaussian noise into seismic data on different level with different intensity, but overall it's allowed us to benchmark the solution and to have this noise generation and removal in kind of controlled and implemented in controlled and measured way. And another thing that basically is kind of one of the pillars of our solution is embeddings. And basically on this slide, we introduce one of the most important part of the system is embedding-based similarity search. And why embeddings and why we actually need embeddings in this kind of pipelines. Seismic data is mostly represented as a 3D structure, and it's not. It contains both noise and real data, and it has kind of structure, overall structural pattern in the data, some kind of texture, some kind of spatial correlation between different parts of the seismic data, and as well as frequency content. And traditional metrics cannot capture all these nuances of the data. That's why we introduced embeddings system here. So each embeddings becomes as a slice of kind of dense vector representation that encodes structural alignment of different parts of the seismic data, noise of the texture, and also global and local dependency within the data and kind of local structure of this data. And In our pipeline, we used this kind of reference embeddings to form experience bank, where this experience bank kind of represents the examples of noisy data, which is labeled, of denoised data, which is also labeled with corresponding parameters of the denoising and type of the noise that was removed. And in the overall pipeline, when a new seismic slice arrives into the system, it's embedded using the language model, specifically visual language model, into a vector. And based on this vector, we can find the most similar vectors within our database, kind of experience banks, would say. And we can retrieve this information to find the most relevant and the most similar seismic data within the database. It's kind of RAG system, retrieval augmented generation, but specifically built for seismic data with some small tweaks dedicated to the specific type of information. And in the whole system, we used this kind of term as residuals. And basically, how seismic experts are working with this data, they're taking a look on the residuals of the data. So residuals is basically the difference between the original and denoised seismic data. And on the residuals, it's basically we can judge whether the results of the denoising were good or not. For example, if residual contains some geological structure, we know that the filter that we have applied was very aggressive and we need to lower a bit some parameters. If residual contains some only high frequency noise and no structure signal, we know that the denoising was clean and we can use these parameters and for the rest of the data. And this residuals allows our evaluator agent compare and remove compare the removed noise with content from our database. And yeah, you can think of it like instead of evaluating the original and denoised image, we evaluating what remains and what disappeared from the original seismic data. And we are basically going to review the agentic system that we have implemented. Yep. The system runs three different collaborating agents that are orchestrated via semantic kernel, and they have used the GPT 4.0. And we have implemented three different agents. The first one is analyst agent. It's kind of domain expert agent that identifies type of the noise, estimates the level of this noise, and it basically uses these embeddings that we have already created. Also, it extracts parameters into some kind of structured format and provides human interpretable reasoning about the noise distribution and structural preservation within the seismic data. And this kind of human interpretable result is kind of important because still the system requires human in the loop to review and validate the result. And human interpretable result is kind of one of the reasons why it should work in scalable environment. The next one is denoiser agent. This agent chooses the denoising algorithm that will be applied to the data. It selects the reduction factors and different parameters of the denoising algorithms. It performs the denoising function directly on the seismic data, and it tracks the history of denoising steps that were applied to the data, because we can have multiple denoising steps and multiple denoising iterations within the data with different parameters or with different denoising tools. And the last one is evaluator agent. This kind of quality control, quality evaluation agent. He compares the residuals that between original seismic data and denoised seismic data, and it compares these residuals within the residuals that we have in the embedding database. And after that, this agent decides whether the system should reprocess, complete, or terminate the processing step. Also, it manages the runtime and economic of the system, and basically judges whether overall iteration pipeline should be stopped or not. And this slide summarizes the whole POC that we have implemented. And we have, during our POC, we have validated several things. The first one is that autonomous noise characterization can be actually implemented and automated within the agentic system, and our analyst agent can reliably identify Gaussian noise and estimate the severity of this noise. Specifically, we have used signal-to-noise ratio, and it has very high accuracy and high consistency across different slices. Second thing is that denoising agent can iteratively adjust parameters, and this history of iterations, it's kind of very helpful here because it helps to adjust parameters of those denoising tools based on the previous denoising factors that we have. So, for example, if we applied very aggressive parameters and our quality control agent tells that there are too much, and we removed a lot of useful information from the seismic data, we need to reiterate, apply lower parameters, and make it much better and preserve more seismic data. And quality control and evaluator agent that was implemented, it's allowed to iteratively improve and update the result. And basically, it helped us to build kind of robust systems that can work even with high noisy and low noise-free images and seismic data. Basically, even if there is a high level of noise, we can, through several iterations, we can remove this noise. And for example, if there is no noise on the seismic data, quality control can tell you that there is no seismic data on the image, so you can skip this processing step. And the next thing is overall overview of the system. Probably I will a bit repeat myself, but it consists of three main agents. The first is analyst, and it basically functions as a senior geophysicist. It performs reference matching using embeddings. It extracts structure and severity of the noise and generates this kind of human interpretable result as long as some kind of metadata for other agents. And the noiser agent is a kind of processing engineer. He applies denoising on the seismic data level. It optimizes those parameters and selects the best parameters to maximize the trade-off between accuracy and noise level removal. And the last is evaluator agent. It measures structural damage and validates quality of the results and drives the workflow to completion or reiteration of further processing. For the orchestration of those agents, we end up using round-robin group chat, and it allowed us to make it kind of iterative pipeline of different agents, but still agents talk to each other and share the information that was extracted from the data. Yeah, I will step a bit on different orchestration approaches that we have tested. So the first one is handoff. And this approach is a bit different from the group chat. In handoff, we have only one agent that is always in control of the system. And this agent delegates tasks to other agents once the processing is complete. Um, and this one works pretty good in some strictly linear pipelines where you have a step-by-step implementation. And it lacked a bit of flexibility for our case because we couldn't have a kind of iterative loop of data exchange and information between different agents. And we ended up using group chat orchestration approach. So all agents share the same conversational space. So all agents can access the information that was generated by agent or language model, as well as wrote the next steps to different agents. Also, this allowed to select dynamically what next agent to use. So, for example, if our quality control agent decides that we need to reiterate or we need to reanalyze the image, we can easily do it using group chat approach. And it allows better and richer reasoning in multi-agent system because, yeah, as I already told you, we can have access to this bunch of information that was already extracted. So we ended up using group chat and specifically round-robin modification of the group chat for kind of strict sequencing between first iteration of the agentic system. And yeah, let's take a look on the overall diagram. So we are starting with the analyst agent, which analyzes images and performs embeddings comparison between different embeddings from our database and query seismic data. And then analyst agent decides whether we need to process it with the denoiser agent or we can, if seismic data is noise-free, we can go to evaluator agent and basically let the evaluator agent decide whether we need to reiterate or we need to finish the processing step. If we go to denoiser agent, this agent can access to multiple denoising functions and select those denoising functions based on the type of noise that analyst agent detected and tune the parameters and select those parameters. And basically, the denoiser agent sends the information to evaluator agent, and evaluator agent can either finish the processing or go back to denoiser to adjust the parameters and reiterate on those parameters. If we step a little bit deeper into analyst agent, for example, we can see that in our embedding database, we have noise-free and noisy seismic data in terms of embeddings. And also this data is labeled. So for noise-free, we have 0 noise level within the database, and also we have increased noise level images with different level of severity of those data, which allow to agent kind of compare and tell exactly what level of the noise is present on the image. And also we have added basically query image. It's two-dimensional slice over three-dimensional data from the seismic data set. And it helped us to build this kind of knowledge database, which basically served for more precise and more detailed judgment over the parameters and type of the noise that we could have. Yeah, also there is a more detailed prompt of the analyst agent that was used, but probably I will skip it a bit. For the processing agent, we basically have used the results of the analyst agent, and then we have used a query image that was then processed using the processing agent. And we have applied denoising based on the description and type of noise that was detected by the analyst agent. Same for the processing prompt. We could have a kind of clarification of the role of this agent, the critical workflow that this agent should follow, and kind of this iteration and tracking the logic between different steps of the pipeline that we have used for this agent. And the last evaluator agent. So this one takes original query image. This is basically also slice over over three-dimensional seismic data. Also, it takes a processed image and it compares the query image to processed image, and as well as with the noised image samples that are stored within the database. And for this agent, we also had same pattern of the prompt that was used for this agent. So role qualification, workflow of this agent, and tracking and termination logic. And basically, we could have three different results from this agent. It's reprocess, and it sends data to denoiser or analyst agent for another round of noise removal or another round of analysis of this result. It could said the processing is complete and we can finish the whole loop, or terminate the process once we reach a limit in terms of tokens or in terms of total iterations. This is a kind of detailed example of coordination between different agents. So on the left, it's lower denoising, where we have very small noise present on the image, and we should have several iterations of denoising. So, for example, on the first step, we have applied 0.1 reduction factor, and on the second, 0.05 reduction factor. So on the first iteration, we removed too much noise and we removed some useful seismic information. So we went for one more iteration with a lower parameter to remove the noise, but still preserve some seismic data. On the right-hand side, there is a higher denoising factor because in this case, we had much higher noise level on the image. And for the first iteration, the noise agent selected 0.1 denoising factor, but the evaluator said that we need to reprocess and apply a higher denoising factor. And on the second iteration, our denoising agent selected 0.3 and removed more noise and made the seismic data much more clear. And regarding the results, here are present on this slide. Again, on the left, it's low noise environment. And again, you could see some visual, a bit better visual appearance of the patterns and traces on this slice. And on the right, it's high noise seismic data. And still, after the loop within this agentic system, we received much better seismic data with more clear traces within the data. Also, we have developed a simple UI, and I will show you just quickly the demo of this solution. Just give me a second while it's loading. So it will go through the data loading, then analyst agent will take part in it and analyze the result. Oh, yeah.
Yeah, I can see.
So yeah, we upload the seismic data, then it's loading into the solution. It takes some time for the loading. Then we are taking a slice over this seismic data and send this slice to analyst agent. And then the analyst agent basically detects the type of noise and severity of this noise. We can see that there is -5 decibel for a similar seismic data. Then it goes to the noise agent. It selected attenuation parameters for denoising tools, and then it goes through evaluation agent that basically said that it's good enough, and we still kind of can optimize those parameters. And again, it goes to the noise agent, which selects a different reduction factor to enhance results. And if we skip till the end, there is a conversation between agents. And in the end, we could see that evaluator agent says there is enough quality, denoising finalized, quality suitable for further analysis. And here you might see the results of the processing and the slice of this seismic data. Or it will not load. Yeah. So, yeah, I'm not sure whether the quality is good, but slice on the right, yeah, has much better traces and texture than original one. That's basically how we approach the solution, how we build it, and how we actually showed that agentic system could be applied to seismic data processing. Yeah.
Yeah,
Thank you for.
thank you, Vladislav. Let me make one final point about this. This is for, I'm sure for a lot of the audience, unless you're a geoscientist or even in the oil and gas, you probably say, "Wow, what is the value? Why should I care about this?" You remember I mentioned at the beginning of the presentation that reservoir recovery, locating the hydrocarbon is one of the most critical things that we do in our business. 1% improvement in reservoir recovery for a company is tens of billions of dollars. Let me give you an example. I was presenting recently to Saudi Aramco. 1% of improved reservoir recovery for Saudi Aramco is worth $180 billion. 1%. So if this technology can help us, in that process, it's one of the technologies, it's not the only technology. But this is what we're trying to do. We're trying to make sure that we improve recovery, we minimize drilling risk, we find a trapped hydrocarbon, and we can do improve field development. It's about the value. We think that this is potentially the step one of many future steps that we're going to take in this business. There's no doubt that this technology has demonstrated that you can improve and accelerate the workflow automation of seismic data processing. And one important point I want to emphasize again is about capturing the knowledge of the experts and encoding it in an agentic system. So with that, if you have any questions or if you are curious about anything, please post in the chat so we will be more than happy to answer them.
Yeah, thanks, Vladislav. Thanks, Hatem, for making that final note. I I see that that was an amazing talk, as you mentioned, for the first step, for the many, many steps to be done. And it's also exciting to see how you can decompose the future impact out of that. And not only future, but I think knowledge capturing is probably the use case applicable not only for energy domains, but any
Yeah.
industrial domain where the same problem exists. So I see that there is only one question in the chat that is highly appreciated from Elena to share the presentation after the talk. So that means that was inciting. And as far as I can see, Elena isn't at SoftServe, so that you can expect that presentation to be shared via email. So if you would have
Well,
any,
one final point I want to make,
go ahead.
Bodan, is that this is clearly a case where collaboration between oil companies and technology companies like us is very important. I can't emphasize how collaborative the work was. This was not a one-sided effort. This was a true team effort. So when we, in the future we want to do more, meaning software, we want to do more of these type of projects where we collaborate with our customers, our partners, and we work. As a matter of fact, speaking of partners, one thing we did not mention that Microsoft was heavily involved in this process as well. We work very closely with Microsoft. It was a triangular effort between us, Chevron, and Microsoft. So this is a model, example of how to do projects in the future.
Very good reference. Yeah, with partners and on both sides, that's probably increase the chances to win. So we have two questions that were asked by the um, people who submitted and registered the event upfront. So let's quickly go through them as we have 5 more minutes. So the first one is regarding the vision of for the future. Do you see agentic AI evolving into a fully autonomous systems that execute seismic processing end to end, or will the human in the loop remain a permanent necessity for quality control and liability reasons?
Well, we
Comment on that.
definitely see definitely a greater degree of automation. There will always be people in the loop. We will never take humans out of the loop because what happens if you're making a very important and expensive decision, let's say where I'm going to drill my next well, right? You're not going to do that lightly based on only what the agentic system will tell you. So there is always humans involved, and at least at a minimum in the quality control of the end results, right? So there is always a human involvement. But we can see a lot of automation. Right now the process is very, very time consuming, and it's very, we do it the old fashioned way. We try this, we try that, we adjust the parameters, fine tune the parameter, change the parameter this way, that way. So this process is really, kind of very manual. So we need to move into that. But we will always have humans in the loop.
That's a fair point. And I see the second question is how are AI agents implemented for seismic data analysis? I think the whole session was dedicated to the session, so I believe
Yeah,
that upfront question was answered. And there is
yeah.
one more question in the chat from Andrew, and let me read that out loud as well. Are there any standards around knowledge capture? I've heard about skill banks, etc., but I would like to know how this is done in AI frameworks.
Well, we have a lot, especially SoftServe. We have a lot of technologies in place. I mean, Agentic is about the workflow automation, right? So how you do step one, step two, step three, and you have multi-agents working together and handing off the results to each other, all of this. But also we have a lot of other technologies like, many of you are familiar with our multimodal RAG, retrieval augmented generation platform that we have done, which we are applying also for a lot of oil and gas application. Let's just say, for instance, for drilling and completion data, where we upload a lot of files and knowledge and information from history, and then the system is able to answer any questions that you have about all your information. We're starting a project very soon with a very big oil service company in the US where they're taking a lot of their failure data for their pumps. We're going to be, I'm talking about tens of thousands of these failure reports from their history for last years and decades. And we're going to be taking all that information to build a knowledge base for them. So there are different technologies. Agentic plays a big role. Gen AI is big role. Multimodal RAG, which is an extension of Gen AI, is playing a big role because it can capture multimodal data. So definitely we are working very a lot on this area of knowledge capture, right? Agentic is definitely one big part of our focus right now, but traditionally, the last few years we've been working extensively on Gen AI and multimodal RAG systems to help us with that.
And just to add on that, we have another customers who implemented knowledge capturing use cases in a similar domain. So one of the options to do that in this kind of SOP, standard operating procedures instructions, that are like just one of the ways to make an output. But as Hata mentioned, that there in agentic workflows there might be many different approaches how to tackle that, as well as to set up the different type of output for those instructions. All right, so seems there's no more questions, but if you do have, don't hesitate to reach out to Hatem or to Vladislav directly in LinkedIn. I know that they're active users of that social media, and yeah, and so looking forward to see all of you at our next R&D talk, uh, probably already in a new 2026. So thanks everyone, thanks Hatem and Vladislav, and
Thank
have a
you.
good rest of the day.
Thank you.
Have a
Bye-bye.
wonderful day.
Have a nice
Bye-bye.
day. Bye.